Hello and welcome to our lesson on ordinary annuities and sinking funds. So an annuity is basically a series of scheduled payments series of scheduled payments made at regular intervals, and the interest is compounded at the end of every interval. So it's very similar to compound interest, where let's say you put in some principal amount and you're compounding 4% interest quarterly. The difference is with an annuity, instead of just putting in some principal amount and letting it sit, and if you so choose, adding to that principal at any point you'd like, with an annuity, every interval that you compound interest, you're also going to be making a payment. So we're going to have a similar formula, but the P in the formula won't represent one initial principal amount. It's going to represent a principal amount. Okay? So what you have is payment periods. You have payment periods and periods of compounding interest matching. Okay, so if you have interest that's compounding quarterly, then you will also be making payments into your annuity quarterly. If you have interest that's compounded monthly, you will also be making payments into your annuity monthly. Now, annuities are typically long-term contracts. So some would consider like a mortgage payment a annuity or an annuity, or you typically will see these with pension payments or long-term savings or retirement accounts. Okay, so this is a long-term thing. So we have this formula, and the formula should look similar to our compound interest formula. Actually, this part of it is our compound interest formula, but because it's not just one principal amount, because there's this recurring payment amount as well as the compounding interest, you got a little additional happening in the formula. So P again represents a payment amount. P represents a payment amount instead of a principal. Okay, P represents the payment amount instead of the principal amount, but everything else in the formula is the same. So A is still the final desired amount. R is still your rate, which will be given to you as a percent, which you're going to plug in as a decimal. N is how many times interest is compounded per year, and also how many payments you make per year. And then T is your time. Okay, so all other variables are the same as they are in the compound interest formula. It's just that P is a consistent payment being made instead of one initial principal amount. So here's an example. Bill is depositing $250 each quarter into an ordinary annuity that pays 4% interest compounded quarterly. So you're making a payment each quarter and you're compounding 4% interest quarterly. Okay, so we want to determine the accumulated amount in this annuity after 35 years. Again, a long-term investment. So our payment amount again is going to be $250. It says that our rate is 4%, and remember 4% translates to 4 out of 100, so I'm going to plug in 0.04 as the decimal, and it's compounded quarterly. Payments are made quarterly, so we know N is going to be 4 for quarterly, and the time for this investment is 35 years. So those are all the variables we need to determine the final accumulated amount. So that's the one variable that's in question. So A is going to equal, and this crazy formula here, we have our payment amount of $250, and then we have a bracket here because there's also a parenthesis. So brackets and parentheses mean the same thing, but it's usually we usually use the brackets after we use the parentheses if we have to just use two in a row. Okay, but they mean the same thing. So we've got 1 plus our rate of 0.04 over our N, which we said was 4, raised to the NT power, so 4 times 35 up here, and then we're going to subtract 1, close that bracket, and all of that is going to be divided by R over N, so 0.04 over 4. That's probably the hardest part, just to make sure you have everything plugged into your formula correctly. From here, the other hard part is typing it into the calculator correctly. Fortunately, Desmos looks really nice for us and allows us to type this in exactly as we see it. So let's make a fraction first, and then by hitting the divide button, and then on the top we're going to put in 250, and then a bracket in the formula. Parenthesis means the same thing. We're just going to use parentheses in Desmos, so it's going to be a parenthesis, and then 1 plus 0.04 divided by 4. And then let's close that first parenthesis. We're going to raise that to, again in parentheses, 4 times 35. Let's close that one. Get out of the exponent. And then we're going to subtract 1, and we're going to close off that last parenthesis. And then on the bottom of the fraction, we need 0.04 divided by 4. So what this is telling us here is that if we make $250 payments into this annuity that's compounding interest quarterly, so we make $250 payments quarterly into this annuity that compounds 4% interest quarterly, and we do this for 35 years. At the end of the 35 years, we'll have saved, well, Bill in this case will have saved $75,677, and because this is money, we're going to round to the hundredths place and say 48 cents. Okay, so the final accumulated amount for making these $250 payments quarterly, that's 4 times a year. After 35 years, you got a pretty good chunk of change saved up there. So that would be a reasonable, I think, a reasonable thing to be able to do, to make $250 payments quarterly. I don't know how likely you are to find an annuity that pays 4%. But if you could, hey, take advantage. Okay. All right, let's try another one here. To save for their grandchildren's college expenses, Ken and Laura invest $500 every month into an ordinary annuity with 6% interest compounded monthly. So you have interest compounded monthly, and Ken and Laura making a payment into this account monthly as well. It says determine the final accumulated amount in the annuity after 18 years. So it's, again, $500 every month, and it's 6% interest every month. So you have a payment amount of $500, and the rate is 6%. That translates to 6 out of 100, and that's 0.06 as a decimal. And compounded monthly, payments are made monthly, so N is 12 because there are 12 months in the year. And this is for 18 years. T is 18, and we're trying to figure out that final accumulated amount. And so let's plug into our formula. So A is going to equal a payment amount of 500 times 1 plus 0.06 over 12 raised to the nt power, so 12 times 18 there, minus 1. Close that off, and then all of that gets divided by r over n, so 0.06 over 12. Alright, so we got it all in there. Now I know exactly what to type into my calculator. So, actually let me just move my, there we go. Make a fraction first by hitting that divide button. So we want 500, parenthesis, parenthesis, 1 plus 0.06 over 12. We're going to raise, oops, got to get out of the bottom of the fraction. Close that, raise that to the, in parentheses again, 12 times 18 power. Out of the exponent, minus 1. Close the last parenthesis, and now go to the bottom of the fraction. So 0.06 divided by 12 there. And they're going to end up with $193,676. And 59 followed by a 7 is going to round that to 60 cents. Okay, so there it is. If they are able to put $500 every month into this annuity that pays them 6% interest compounded monthly when they make those payments, after 18 years, they'll have saved up almost $200,000 for their grandkids. Now, $500 a month, that's pretty steep, so is 6% interest, but again, worth doing if it's something that you could afford. Okay? So just to get a grasp on what's happening here, if they made $500 payments every month for 18 years without any interest, how much would they have accumulated? So $500 per month, so times 12, for 18 years, that would be investing $108,000 of their own money, right? So if they ended up with $193,676 but only put in $108,000, then by doing this, they've earned almost $86,000 in interest, which is pretty impressive. Okay, now let's look at that in the first one. I forgot to do it. If Bill was depositing $250 every quarter, so $250 four times a year every quarter for that one was 35 years, then he's put in $35,000 of his own money. So if he ends with $75,677 but only put in $35,000, then he's earned himself $40,000 interest. So he's earned more in interest than he put in himself, if that makes sense. Okay, so these annuities are good ways to save money if it's a long term. The longer you can make the payments and let the money sit there and accrue interest, the better off you're going to be. Okay, now a sinking fund is basically a reverse annuity. So think of a sinking fund as a reverse annuity. With an annuity, which the ones that we just looked at, you're choosing your payment amount. So maybe you decide that you can handle $250 a month to pay in, and the final result is going to vary depending on how long you make the payments, so what the time period is for your annuity. With a sinking fund, what you're going to do is you're going to choose your final amount. So let's say you know that you want to save up $20,000 for a car, or let's say you know you want to save up $80,000 to put down on a house when you retire, or to pay off your house when you retire, something like this. If you know your final desired amount, then you can use another version of the formula to calculate the payment. So you choose your final amount, and then the payment is predetermined for you. So since we're going to know the final desired amount, this version of the formula we're going to look at can be used to calculate a payment amount. So notice this version of the formula has all the same components, but instead of A equals, where we're finding the final amount, it's P equals, where we can calculate the payment amount. Okay, now let me just take you back to that other formula for a second so you can see. If we wanted to take this formula and solve it for P, okay, if I wanted it to be P equals, first there's this division by R over N, so I would multiply both sides by R over N, multiply by R over N here, and those would cancel. Okay, so we would have A times R over N equal to P times this whole thing that's in brackets, right? So if I wanted to solve for P, I would have to divide over that whole thing in brackets, and that would be my formula. P is going to equal A times R over N over the whole thing that's in brackets, and that's exactly what we see on the other side of our notes here, on the next part of our notes. So if you look here, again, we have A being multiplied by R over N and then divided by the whole thing in brackets, so that the formula is P equals. So this formula calculates the final amount, and the other version of the formula, so this calculates the final amount knowing the payment amount, and the other version of the formula calculates the payment amount knowing the final amount. So this calculates the payment amount knowing the final. Okay, so for example, we've got Richard. He would like to save $30,000 in 5 years to buy a new grand piano, and he decides that instead of just saving the money on his own, he wants to invest monthly into a sinking fund that pays 4.5% interest compounded monthly. So he's going to make payment. He knows he wants to get to $30,000. What we have to do is figure out how much he's going to have to invest in this sinking fund every month. What is the payment he has to make monthly to accumulate $30,000 in 5 years? So again, you have to be careful because remember we had the compound interest formula where it's just some principal amount, and there was the present value formula where we get that final desired amount, but it's just one principal. Here we're making in payments. Okay, so we have a final desired amount, change back to blue here. Final desired amount is $30,000, and we're going to be looking at making monthly investments at 4.5% interest. So the rate is 4.5%. That translates to 4.5 out of 100. And if you forget, remember that's the translation. Percent means out of 100. So you take your number, put out of 100, and then you can use Desmos to convert that to a decimal. So that's how I'm doing that in my head, but that's how you can do that if you need your calculator for assistance. So 0.045. Compounding the interest monthly, making the payments monthly, means n is going to be 12, and the time here is going to be 5 years. So we have to figure out what is the payment amount. Every month, how much is he going to have to put in to get to his goal of $30,000? Okay? So P, this time, is going to equal 30,000 times R over N, so 0.045 over 12, and that will be divided by bracket, which is the same thing as a parenthesis, 1 plus R over N raised to the NT power, so 12 times 5 there, minus 1, and then close that off. So let's see what the payment amount is going to be. So we have, get rid of all this, make a fraction with the division, 30,000 times R over N, 0.045 over 12. Close that one off, and then on the bottom, parenthesis, 1 plus 0.045 over 12 again. Let's get out of the fraction, close that parenthesis, raise it to the, in parentheses again, 12 times 5 power, close that, get out of the exponent, subtract 1, and close the last parentheses. And there it is, $446.79. So that is the payment amount he's going to have to put in every month in order to accumulate $30,000 at the end of the 5 years. Now, again, let's think about this. If you made $446.79 in payments every month, geez, 7, 9, okay, so every month for 5 years, then he's only putting in $26,807.40 of his own money. So he's getting about $3,200, or earning about $3,200 in interest. Now that's not near the amount of interest that he was earning on the first two problems, or that we looked at earning in the first two problems, and that's because those investments were a much longer term than 5 years. But still, if you're saving money on your own, right, making the same payment amount every month for 5 years, you're only at $2,700, where, you know, there's an extra $3,000 in interest earned if you put it into an annuity. Okay, so things to consider. All right, we got one last one. If you want to try this, I think this would be a good place to pause the video. Otherwise, let's see, Becky, she wants to be a millionaire in 20 years. Who doesn't, right? How much would she need to invest quarterly in a sinking fund paying 8% interest compounded quarterly to accumulate $1 million in 20 years? So this is a final desired amount we know of $1 million. And again, not the present value formula where we just put in one principal amount, but we want to make payments in every time interest is compounded. So we know the final desired accumulated amount is $1 million, and interest is going to be accumulating, let's see, oh, it's 8% interest, so 8% translates to 8 out of 100, which is going to be 0.08 as a decimal. Compounded quarterly, payments are made quarterly. This was, sorry guys, why did I put N there? This is R. N would be quarterly, that's 4, and time is 20 years. That's a much better term. What is the payment amount that Becky's going to have to make in order to reach her $1 million goal in 20 years? Okay, so P is going to equal $1 million, should get all those zeros in there, times R over N, so 0.08 over 4, and then that's all going to be divided by 1 plus R over N raised to the NT power, so 4 times 20 minus 1, and let's get this into the calculator. So we are looking at, again, make a fraction, 1 and then 6 zeros, 3, 4, 5, 6 times 0.08 over 4. And then on the bottom, parenthesis, parenthesis, 1 plus 0.08 over 4. Out of the bottom of the fraction, raise that to the 4 times 20th power. Get out of the exponent, subtract 1, close that off, and that is a hefty payment. $5,160, and that's going to round to 71 cents. So if she can manage basically a $5,000 payment 4 times a year, then she can get to that $1 million in 20 years with this particular sinking fund. Let's see, how much is she putting in of her own money? So if she puts in $5,160 4 times a year for 20 years, guys, look at that. So it seems like $5,000, that's a pretty hefty payment to make. I couldn't do it. There's no way. But if she can do it 4 times a year for 20 years, she's only putting in $412,800-ish of her, as I left off the change, of her own money to get to $1 million. She would be earning, look at that, if she's trying to get to $1 million, and she only puts in about $412,000 of her own, she's earning $587,200-ish. Again, I left off the change. That's how much she's earning. She's earning more in interest than she's putting in, and that is a significant amount of interest. So obviously, the higher payment you make, the higher the rate, the more often the interest is compounded, and the longer the term on the loan, the more interest you're going to be able to accumulate. Okay? So if you can predetermine a payment amount, then you can end up with some final desired amount that could be calculated. If you know the goal of where you want to get, then you can calculate a payment amount to reach that goal. So we have the annuity formula and the sinking fund formula to do either one of those things for us. So I think that should be enough to get you going on your practice, but as always, if you need some additional help, then just reach out. All right, guys, take care.